So welcome everybody to the American Spinal Injury Association, our early career clinician and researcher webinar series. In this webinar series, we're looking to provide a bench to bedside view of spinal cord injury research and medicine through the eyes of early career professionals. Today, we are going to be hosting Dr. Patrick Ganzer and Dr. Roberta Vastano as they talk about their research relating to neuromodulation and spinal cord injury. So a little bit more about this series. It's a multi-part series that features episodes focusing on a single topic relevant to spinal cord injury research and medicine. In each episode, we try to include two different types of presenters, ideally one perspective being more a lab focused and one being more clinician focused. Each presentation is about 20 minutes with the following 10 minutes for question and answer. Beyond sharing the emerging work of the young professionals in spinal cord injury, we also aim to first identify and archive the rising stars in this space, and two, create a community for networking together as people based on a common mission. So we are here today for season 1, episode 4, titled Neuromodulation. And a little bit about our first speaker. Patrick, I'll stop sharing so that you can open up your slides here.
Okay.
All right, this is Patrick Ganzer. Patrick is going to talk to us today about reactive bioelectric medicines. He received his bachelor's in neuroscience from King's College and his Ph.D. in biomedical engineering and science at Drexel University. He's now currently working with the University of Miami, jointly appointed at the Miami Project to Cure Paralysis and the Department of Biomedical Engineering. Dr. Ganzer is currently a PI at the University of Miami, where his lab focuses on preclinical neural engineering research. He has spent significant time working in both academia and industry, creating and deploying translational neurotechnology. His neurotechnology teams have published in several high-impact journals, including Cell, Nature Communications, Science Advances, and eLife, with their work highlighting in the popular press, being highlighted in the popular press in US News, Wired Magazine, and MATLAB. And it's been translated to multiple clinical trials. So Patrick, we're really excited to have you here today and look forward to your talk. Thank you.
All right, thank you, Annie. My audio is okay and screen is sharing. Okay, fantastic.
That's good.
Excited to have everyone's time to give, I guess, a little bit of a shorter talk, try to cover some ground on some of the group's work in the realm of reactive bioelectronic medicine. So we're talking about really throughout closed loop nerve stimulation. A little bit more structure for the presentation. So first introduce, really what is a bioelectronic medicine. I think some of you already know this. These are stimulation devices that can be kind of open loop or pre-programmed, or maybe even a little bit more challengingly, closed loop and reactive, powered by an algorithm or something else that reacts to a given state, stimulates a nerve, and maybe can provide more optimal therapeutic benefit. I'll be focusing really on two different applications of closed loop nerve stimulation, really focused on vagus nerve stimulation, or VNS. The first of which is to treat upper limb dysfunction following cervical spinal cord injury. This is started in rodents during my postdoc and is now very excitingly in phase 1 clinical trial for individuals with cervical spinal cord injury. And the second, to wrap up the talk, application of closed loop VNS is going to be for treating spontaneous myocardial ischemia. And then we'll have time for a Q&A at the end. So some of you may already know this, but what is a bioelectronic medicine? So it could be contrasted with good old molecular medicines, and Advil, Pepto-Bismol, you name it. Depending on its route of administration, Molecular medicines can have a lot of off-target effects, right? If they get into the bloodstream, into tissues where they really don't need to be, leading to side effects. It'd be really nice if pills can be almost instantaneously active, providing benefit instead of waiting X minutes for them to kick in. And also it'd be really nice to turn them off rapidly as well, instead of them wearing off metabolically. So bioelectronic medicines can address some of those shortcomings by using nerve stimulation to treat disease and affect physiology. So depending on which nerve you want to stimulate, you can then have more targeted release of a given set of molecules, maybe in part of the heart, part of the stomach, part of the brain. This should mitigate side effects. And in some instantiations, bioelectronic medicines and stimulation, the effects are almost instantaneous. So you can get really rapid control of on and off cycles, and even trigger stimulation when needed. So these are some hopefully attractive components of bioelectronic medicines. So the first part of the presentation will focus on using vagus nerve stimulation to hijack and really enhance neuroplasticity. VNS, or vagus nerve stimulation, is now FDA approved for a number of disorders, including depression, obesity, and more recently, stroke, for enhancing rehabilitation. This is what the interface looks like. Sorry, it's a little bit of an intraoperative photo. So it's about a half-hour procedure. So you're in and out, outpatient. And although the vagus is connected to many organs, at the cervical level, the vast majority of the fibers are afferent, about 85 to 90%. And when you stimulate the cervical vagus, there's a lot of feed-forward excitation to many different neuromodulatory nuclei, including locus coeruleus and nucleus basalis. That gives you rapid release transiently of plasticity-promoting neuromolecules like acetylcholine and norepinephrine. And so if we have electronic control of this, we can potentially strengthen existing synaptic connections, grow new axons, and this may be formidable if there is a spinal cord injury or stroke or damage to a neural circuit, where you might want to regrow connections back to muscles or target tissues for therapeutic benefit. So we call the construct targeted plasticity therapy. So using vagus nerve stimulation paired with different events during therapy. This was now gained a lot of support generally, as bioelectronic medicines have. Originally at DARPA, two programs founded by Doug Weber were electrics, so electrical prescriptions, as well as TNT, targeted neuroplasticity therapy. The NIH has Spark, and there's a number of different programs now focusing on this kind of therapy. So if we have temporally precise control of these plasticity promoting neuromolecules, we could potentially pair them with a number of events, including sensory motor events, which is really the focus of the first study here I'll show in a second. As we all know, when we activate, in this case, an upper limb, we have motor cortex and distributed neural circuits there active. If you pair that neural activity repeatedly with brief bursts of vagus nerve stimulation, so it's their neural activity coinciding with plasticity promoting neuromolecule release, 1, 10, 100,000 pairings, you can get really robust expansion of the active neural circuit. And this may be desirable if you have part of this control circuit taken out by an injury like a spinal cord injury. So fast forward to some of the exciting clinical work. Won't go over really the preclinical work that led to these clinical trials, but the depiction here is of the application of vagus nerve stimulation to enhance rehabilitation after stroke. So this is in the inset, the cartoon of the implant. So patients will come in for rehabilitation with a physician when good movements occur and therefore desirable neural activity that you want to reinforce. The physician will trigger nerve stimulation. This is how it's kind of closed loop and paired to potentially enhance the effects of rehab and enhance neuroplasticity. So the phase 1 clinical trial for this application was very promising, published in 2016. On the y-axis is the Fugel-Meyer score. So that is how well can you move your arm and hand. And in the red group, which received many pairings of VNS with movements during rehab, you got about a 3 to 4-fold improvement over rehab alone, therefore giving some evidence that this can be a rehabilitation enhancer. Fast forwarding to the phase 2 clinical trial published in 2018, see similar effect sizes, a little bit more blinding, and in a crossover group where the rehab group, which has the implant but it's not active, crossed over to VNS rehab and had a really almost identical enhancement of the effects of rehab. And lastly, the pivotal trial, which was published late last year, also showed clinically meaningful effect sizes where VNS recovered more arm and hand function compared to rehab alone in over 100 patients in this study, leading to FDA approval, which is the first neurostimulation therapy ever FDA approved for stroke. So this is very exciting and a big win for bioelectronic medicines. While this was developing and translating to the clinic during my postdoc at UT Dallas, we also started to look at different injury models and potential, injury conditions that this therapy could potentially be used for to promote neuroplasticity and recovery. So I'll overview some of this preclinical work published in eLife, where we used a combination of different kinds of spinal cord injuries, unilateral or midline contusions at the cervical level, that would again insult circuits, and potentially we can use VNS targeted plasticity therapy to promote plasticity of these damaged circuits and get more connections back to paralyzed muscles. A quick overview of the methods that we use. Again, this is preclinical research in rats. To model upper limb rehab, the animals are introduced to an operant conditioning task where they learn to reach out and pull on a handle, where we monitor the amount of isometric pull force. So you get a lot of rich data. The animals engage in hundreds and thousands of trials every week, and we can monitor really their peak force, peak torque, and other correlates of forelimb function. And this is how we also isolate and identify good movements for closed loop vagus nerve stimulation. This is a depiction of the cuff placed around the rat's left cervical vagus and some of the stimulation parameters. When a good movement happens, we trigger a brief burst of vagus nerve stimulation, or just give the animals rehabilitation alone with no closed loop VNS. So the work I'll overview really quickly is, and then get into some of the latest kind of clinical trial developments based on this work. Was published in eLife. And this is a depiction of some of the team members, a really fantastic multidisciplinary team down in UT Dallas at the Texas Biomedical Device Center. Biomedical engineers, also histologists, electrical engineers, and the PIs, and really the inventors of this therapy, Mike Kilgard and Rob Renick are depicted here. So if we have a closed loop bioelectronic medicine, it should follow some temporal rules. And if we can actually give temporally precise medicine, how precise do we have to pair VNS, in this case, with movements during rehab? So we assessed this hypothesis after a unilateral hemicontusion in rats in this study, where the animals on the y-axis here before lesion can pull at peak about more than half their body weight. After an injury, this drops down, and then we stratify the animals into 3 different groups. If you pair VNS repeatedly with the best 20% movements for about 6 weeks, the animals recover a reasonable amount of function. They don't get back to pre-lesion, but they get close. If you give animals just rehabilitation, they recover some function, but it's significantly lower than the VNS plus rehab group at the top 20% trials. And if you pair you give the same amount of VNS as the red group, but you pair it with the 20% worst movements, so they're getting the same amount of vagal nerve stimulation, just paired differently, they are no different than rehab alone, which is really interesting. If you break this out a little bit further, the highly precise VNS pairing gets about 60 to 70% benefit over rehab. If you delay VNS by 2 seconds from the best movements, you start to get a dip in the benefit over rehab. And the black group, which received the same amount of VNS, was also having VNS paired with good movements, but separated in time by about 25 seconds. So there seems to be a window of opportunity to promote recovery, and further studies may be looking at filling out this function to see exactly, what is the decay of this window of opportunity for pairing VNS with movements to get recovery. We also followed up in this study looking at neuroplasticity. So same injury model, drop in strength. We then paired the best 50% movements in red with vagus nerve stimulation, again, seeing another enhancement over rehab. At the end of therapy, vagus nerve stimulation is turned off to look at the potential lasting effects. And in these animals, we then assayed potential correlates of functional neuroplasticity and panel B using intracortical microstimulation, where you can derive pretty high resolution brain maps, stimulating different areas, elicit different movements. And the take home message there is that animals that have more recovery of forelimb strength have about 4 to 5 times more area of the brain connected to the paralyzed grasping muscles. So this is some of the first evidence of neuroplasticity preclinically using this kind of therapy. And we also looked at neuroanatomical plasticity using pseudorabies virus. So this is a transsynaptic neural tracer injected into the paralyzed grasping muscles below the level of the lesion. Over time, this transports retrogradedly back to the cerebrum. Each little black dot here is a cell. And the agent has the infected neurons express enhanced green fluorescent protein. And so looking at cortical and subcortical and spinal sites, the story here generally matched the brain mapping data such that animals that received closed loop vagus nerve stimulation repeatedly during rehab had an enhancement throughout of connections from the brain to the paralyzed grasping muscles. We did not see any subcortical plasticity in this injury model. We could refer to the eLife paper for different assessments of other nuclei in the spinal cord and brainstem. So the last thing I'll mention on this front before jumping into the last few slides on myocardial ischemia is the clinical state of affairs for translating this therapy to spinal cord injury. So can we improve access by having individuals maybe use this type of construct at home via automating delivery and again to new conditions, maybe even beyond spinal cord injury? So these questions started to be assessed at the end of my postdoc, funding from Wings for Life, DARPA, the Caruth Foundation. If you have any questions about the therapy, the Texas Biomedical Device Center is really building out an awesome portfolio of these technologies for using closed-loop VNS to treat a number of disorders. To address the take-home need, they created the replay system, which is a suite of sensorized objects that patients can interact with to manipulate and monitor very accurately the state of the hand, the amount of force that's being applied to the objects. This is a way to monitor what the hand and arm are doing without a physician present to potentially close the loop and deliver nerve stimulation. They also did a significant amount of work miniaturizing the device by over a factor of 10, making it batteryless as well. So it's wirelessly powered and and stimulation is delivered in the software through an Android device. And the clinical trial is now registered and recruiting and ongoing for, again, it's a phase 1 for individuals with cervical spinal cord injury. The rehab system in the take-home version is shown here in the video, where you can get through many sensors, in this case, just an accelerometer, as well as a force transducer, the state of the arm and hand. This is also integrated into a gamified rehabilitation construct to hopefully make rehab more exciting. And this is a way to, again, to monitor the state of the arm and hand to deliver VNS. So Dr. Rita Hamilton will be presenting at the main conference here in a few weeks at the end of the month. Some of the most recent phase 1 clinical trial data, looking at grasp, outcomes, improvement of arm and hand function, and safety. So if you'd like and you're attending the conference, you could see her talk and hear more on the latest. In closing here, there's of course other applications for vagus nerve stimulation in the field. There are many, many. The vagus is connected to many organs, including the heart. And so in the last little few slides here, I'll introduce some of the team's recent work on using closed loop vagus nerve stimulation to modulate cardiovascular states and really a kind of myocardial activity. This was recently published in Science Advances. I'll have a grand challenge of going over this in just 1 or 2 slides. Again, a nice multidisciplinary, talented team at the helm here, working on things like machine learning, biomedical engineers, neural engineers, cardiovascular physiologists at many sites, including Battelle Memorial Institute and Q-Test Labs. So cardiovascular disease is accompanied by many things, including myocardial ischemia, which is happens when there is a decrease in oxygen supply and or an increase in demand. This, of course, can lead to symptoms like angina/chest pain, or it could potentially be asymptomatic, where you don't even know it's happening. One thing that's underappreciated is that the vast majority of myocardial ischemia events are asymptomatic. So this is a huge problem, right? Your heart is suffocating, cells are dying, and you don't have any conscious awareness of this. This could be an opportunity for algorithms, again, reactive bioelectronic medicines to be introduced and potentially treat myocardial ischemia. So it's a cartoon schematic of how we kind of went about addressing this problem, again, preclinically, by collecting different cardiovascular biosignals, ECGs, blood pressures, and so forth, feeding these into artificial neural networks and advanced machine learning architectures so that we can close the loop and potentially trigger vagus nerve stimulation when the heart is stressed and maybe on the verge of cell death and damage. VNS is attractive for this context, such that it could potentially decrease chronotropy, inotropy, therefore reducing myocardial oxygen consumption and potentially even mediating coronary vasodilation to get more blood to the heart when needed. And so this is an overview of the problem and really how we address this. And so really last slide here, this is a cartoon schematic of really the main findings and the main way we instantiated this in the study, where algorithms that are operating at roughly 90% accuracy were in charge of delivering hopefully therapeutic vagus nerve stimulation, or we made these open loop. So in panel B, we tested these hypotheses across 3 different experimental conditions. The first of which is just ischemia alone. So it's a bout of robust heart stress that can lead to arrhythmias and cell death. The second group in red is putting the algorithm in charge of closed loop vagus nerve stimulation, such that when it senses ischemia, it triggers VNS to hopefully slow down the heart, mitigate myocardial oxygen consumption, and prevents any damage to the myocardium. The last group in magenta is really one of the most common bioelectronic medicine delivery systems, which is open loop, where the stimulation is pre-programmed and therefore may miss spontaneous myocardial ischemia events. The main effects here are in closing are in panel C. So electrocardiographically, the ST segment, which occurs during ventricular repolarization, becomes depressed during ischemia. If you put VNS, a closed loop VNS active, again, powered by artificial neural networks and machine learning, you can mitigate this electrophysiological abnormality indicative of subendocardial ischemia by decreasing heart rate, decreasing afterload, and overall decreasing myocardial oxygen consumption. This is a rate pressure product. If you have an open loop system, again, that can miss the spontaneous events in magenta, there's almost no effect on these cardiovascular states. It really is late to the party or misses the events in general. And so this is the main effects from the study. If you'd like to take a look at the full paper, ask more questions during the Q&A. It was just published this last January. So there's a lot of closed loop artificially intelligent medicines coming into the fore, into the clinic. There are many companies, including NeuroPace, which is a closed loop DBS system for preventing seizures. We already heard about the targeted plasticity therapy work, VNS plus rehab for stroke, spinal cord injury, and maybe other conditions. Algorithms are starting to reach the level of clinician performance in detecting things like ECG abnormalities. There's many systems now for radiology, oncology, that can use advanced machine learning for image diagnosis to help physicians make decisions. And it sounds a little Star Trek-y, but there's actually 30 FDA-approved artificially intelligent medical devices now in the clinic, helping patients, helping doctors, and so forth. So very excited for the future of closed-loop bioelectronic medicines, and hopefully you got a good taste of some of the work the group has done, the groups have done here really in the last few years. So lots of people to thank at Texas, including, again, the Texas Biomedical Device Center, who is really making a mark in the field of closed-loop VNS for treating disease. Battelle and QTest Labs played intimate roles in the cardiovascular work you saw. And lastly, very excited to be at the University of Miami and the College of Biomedical Engineering and the Miami project to continue a lot of this work. So thank you for your attention, and I guess we'll open it up for questions.
Thank you so much, Patrick, for that great talk. I just let people know that they're allowed to ask questions in the chat, or if you'd like, we'll take a couple minutes right now to ask Patrick some questions. If you would like to unmute and share or unmute yourself, or if you'd like to ask that question.
Hey, Patrick, it's Greg. Cool stuff. I had
Thanks.
a quick question about the VNS and the ischemia model that you used.
Yes.
There, did you so you're inducing ischemia?
Yes.
Correct. For how
Yes.
long?
So we induced from rest and transition to ischemia and ST segment deviations in the paper for roughly 2 to 3 minutes. So it's really the acute period.
Right.
Yeah.
So that's really what my question was. I wonder chronically, like if you think of chronic ischemia, because that has real corollary to, you know, chronic diseases, which is really how it presents, unless someone's gonna die of a heart attack. But you know,
Right.
so I was wondering, are there chronic paradigms that you could use, and what would be the biological, I guess, tissues you could look at and then make a parallel to something clinical? And the reason I ask, I think, is because in the mouse model, there is, well, I ask him in part because in the mouse model, you have knockouts that give you hallmarks of disease, and it might be something really cool to test if VNS has an effect on actual heart or extant disease. That was a mouthful, sorry.
Oh yeah, this is a fantastic question. So these, you know, these are rats. So I think you're probably referring to like ApoE knockout mice and things like that would have like a
Correct.
maybe an atherosclerotic background, right, and vasculopathy.
Yeah.
So if the algorithm can detect ischemia, it probably should act right away if this was prolonged ischemia and it was maybe late to the scene, we did not study that scenario. So although it's, is acute ischemia, is there a window of opportunity? I guess that's kind of maybe something you're poking at. That remains to be studied in future investigations. If this was more of a chronic diseased rat that maybe was, had a Zucker fatty rat background, cardiometabolic syndrome or something like that, or ApoE knockout, then, VNS, acting on that diseased myocardium, again, remains to be seen. What can you do when there's more disease on board? I think excitingly, VNS is also anti-inflammatory. And so we know there's a huge role of inflammation and atherosclerosis. That's obviously more of a chronic set of effects, right? So, yeah, remains to be determined regarding really, can this work in more of a diseased chronic animal? But starting off looking at the system, the algorithm, and kind of proof of concept, that's a lot of the points that the study hits here.
Right, cool. Anyways, we can chat more about it.
Yeah, great question. Thanks.
Thank you.
All right, if there are no other questions right now, we'll try to stay a little bit on track. So Patrick, again, thank you so much for your talk.
Thank you.
And Roberta, if you'd like to start sharing your screen, I'll give you your little intro here. So Dr. Vastano will be talking to us today about mechanisms of multisensory integration and body representation in spinal cord injury. She received her master's degree in cognitive and experimental psychology in 2012 and her Ph.D. in bioengineering and robotics in 2017. She is currently affiliated as a postdoctoral fellow in the Department of Neurological Surgery at the University of Miami and the Miami Project to Cure Paralysis. Her mentor is Dr. Eva Wierstam-Noga. After receiving her master's degree in cognitive experimental psychology from the University of Gabriele D'Annunzio.
Correct, yes.
Dr. Vastano earned her PhD in bioengineering and robotics at the Italian Institute of Technology in 2017. Dr. Vastano is currently working on multisensory body representation in individuals with spinal cord injury. She has had research funding supporting from the Craig Nielsen Foundation. The focus of her current research is on the ability to integrate cross-modal information known as multisensory integration following spinal cord injury with and without neuropathic pain, and how the multi-dimensional concept of multisensory body representation is affected following spinal cord injury. She uses techniques like EEG, chronometric methods, TCDS, and bodily illusions. So Dr. Vastano, Roberta, thanks for joining us. And
Thank you for the introduction.
Before you get started, I just want to, if anybody has questions throughout the talk, or if anybody has questions that they weren't able to ask Patrick, feel free to put them in the chat and we'll get to them at the end of the talk. So go ahead. Thank you, Roberta.
Thank you, Annie, for the introduction. Thank you all for attending my presentation and giving me the opportunity to share my research. So today's talk will be on the mechanism of multisensory integration and body representation following a spinal cord injury. Apologize. So I will mainly focus on these two main topics, multisensory integration and body representation, towards my presentation. And towards the end, I will explain some methodologies to manipulate body representation using visual illusions and transcranial recurrent stimulation. So let's get started with the topic of multisensory integration. Multisensory integration is the process by which we integrate stimuli that come from different sensory modalities. This process is important because it has a facilitatory effect on perception and action. It is also a quite complex process and is elaborated by different areas in the brain. These, for example, can be sensory specific areas like the somatosensory cortex, auditory, and visual cortex. They somehow have some neurons that can respond to multiple sensory information, as well as there are some cross-modal regions, more high-level regions that we call non-sensory specific multisensory areas that also contain multisensory neurons that respond to cross-modal stimulation. This could be, for example, the posterior parietal cortex, part of the prefrontal cortex, the posterior superior temporal sulcus. So we have recently proposed a theory in which we believe that as an opposite effect on multisensory integration, spinal cord injury may present multisensory depression and a competition mechanism. And this is because due to several reasons. So first, there are motor, proprioceptive, somatosensory impairments following the injury that can make multisensory integration very challenging. There may be reduced experience with cross-modal cues, and this brings in discussion the unisensory imbalance topic. So there are some unisensory information like somatosensory that can be very weak. And so they may be not properly integrated both at the non-sensory specific and non-sensory specific level. While there are some other information like auditory information that can be more dominant, like for example, if you think about exaggerated startle reflex in spinal cord injury. So this unisensory imbalance may create some complication to have an intact multisensory integration, both at sensory specific and non-sensory specific level. Then there are also deficits in GABAergic inhibition and dysfunction in lateral inhibition that are also important. They need to be intact in order to have a proper multisensory integration. And finally, there could be also reduced responsiveness to cross-modal cues in general in multisensory areas. So we were interested to test this hypothesis in spinal cord injury. We perform a multisensory integration task. A way to test multisensory integration is to perform a detection task in which we deliver redundant signal information. This signal can be unimodal or bimodal or trimodal, as long as they appear either temporally congruent or spatially congruent, so either in the same time or in the same space. We chose the temporal congruence task, so we asked our participants to attend one of the stimuli. The stimuli could be visual, auditory, or tactile, or a combination of them, audiovisual, visotactile, and audiotactile. They were just instructed to respond vocally as fast as possible to any of these stimulation. As a consequence, this kind of task, as a result, we have the so-called redundant signal effect, basically bimodal information, as I said, as a facilitatory effect on perception and action. So participants are faster to respond compared to unimodal. And we do find this in both groups. However, to study multisensory integration, we need to adapt other statistical procedure. The most used one is called independent race model. Here we are observing a cumulative distribution functions in A and B in control participants and SCI in the visotactile condition, the green line. So as you can see, we have the tactile information alone, the visual information alone in both groups. And then we have the bimodal information that's faster than the unimodal. And this is the classical redundant signal effect. Both groups are faster in the bimodal. However, when we compare the bimodal condition to the race model, which is a predicted model based on the sum unimodal minus the their product, the unimodal responses minus their product, we, in order to have a multisensory integration, the visotactile condition in this case needs to be faster than this predicted model. And we do find this effect in control participants. As you can see, the colored line is faster than the race, and we fail to find this in SCI participants. The figure C here shows better these effects as we show the violation of the model, meaning the difference between the race and the visotata condition. So all the values above 0 are considered to be integration mechanisms. Everything below 0 are either depression or competition mechanisms. So you can clearly see a reduced multisensory integration in the spinal cord injury group. We find this in all the other conditions, either audiovisual and tactile. We do have evidence of a computational model approach that I do not have the time to show you here in detail, that these effects happen for two reasons. One is a reduced silence. So participants with SCI perceive certain stimuli with reduced silence, and this usually occurs when the reaction times are faster. And with increasing reaction times, these effects start to decrease as they have competition mechanisms. So the stimulus starts to compete to access to the motor system, for example. And we found that the greater competition with increasing the reaction times. So the conclusion are that we found the multisensory integration deficit in spinal cord injury participants. The main reasons are, one is that response selection is a competitive process in a competitive environment. So SCI participants may perceive certain stimuli with reduced silence and higher perceptual load. Then also motor depression and unisensory imbalance that's generated by sensory motor deficits and brain organization following the injury can trigger multisensory integration deficits. However, for this assumption, we will need the brain data, and this is something I'm working on it. I'm actually collecting the same experiment using the EEG to show the difference between our groups using event-rated potentials. Now I will move to the topic of body representation. It's important that you do not perceive these two topics as separated, because in order to have a coherent body representation, we will need an intact multisensory integration. So body representation, it's a multidimensional concept. So as I said, it requires an intact multisensory integration, so intact perception through our senses, intact integration of proprioceptive, interoceptive, vestibular inputs, as well as an inner construct of the body that comes from our memory. So all these components shape this complex concept of body representation. Now in laboratory settings, we can divide the concept of body representation into dimensions in order to study the body schema and the body image. The body schema is a more plastic sensory motor representation of the body and is essential for action. For example, we can study this asking participants performing certain tasks in which they have to engage the sensory motor system. For example, if I ask you to tell me if what you see on the screen is a right or left hand, in order to give me a response, you need to mentally rotate internally these hands to 0 degree to tell me that that's a right hand. For body image, instead, we mean a more abstract and semantic concept of belief of the body. This could be tested in laboratory settings. For example, if we ask participants to match their body size with one of these silhouettes on the screen. Now, when we bring this to the SCI world, we have several factors that can be impaired. So as I showed, the multisensory integration is impaired. So part of the perception is impaired. There is evidence on proprioception and vestibular mechanisms that are impaired, as well as sensory motor integration. So spinal cord injury may heavily alter body representation due to sensory motor deficit and cortical remapping. So our aim was to investigate these effects. So consider, for example, that so far we showed deficits in multisensory integration as something more automatic and low level, a sensory that can be impaired, while here we show evidence on body representation that's based on multisensory integration, but is an effect that relies more on high-level cognitive functions. So we tested body representation in our participants, performing a laterality judgment task or a mental rotation task of body part. They were instructed to observe a stimulus on the screen that to provide as fast as possible a vocal response, telling us if what they observed was a left or right stimulus. The stimulus on the screen could be a hand or a foot, or a control stimulus represented by this little duck. But stimuli, all the stimuli could be left or right and oriented in two different orientation. An easy orientation, 75 degrees, and a difficult orientation, 150 degrees. So the rotation mechanism would help participants to engage the sensory motor system to provide a response. We focused on two brain measurements, event-related potentials and event-related spectral perturbation of alpha beta. Here we are observing just a map of electrodes on the scalp. This is the front part with the eyes and the nose. We were interested in three main components for event-related potentials. Sensory components, so more low-level perceptual components by looking at posterior P100 and 200. Are more high-level cognitive components, so late components that happen after 300 milliseconds, for example, and this is so-called rotation-related negativity, and some of the attentional component that we call here frontocentral N100 and P200. So this positivity and negativity happen within this time that I present here, this time frame in milliseconds, and all these components are stimulus locked, meaning that in the results that I will show on 0, I will have the presentation of the target. Similarly, we look at event-related spectral perturbation, stimulus locked. We go look at alpha beta frequency over the motor cortex and the vertex. So these are our results. For early potentials, we found a lower P100, so lower positivity that peaks 100 milliseconds after the onset of the stimulus in SCI participants compared to controls. We found a general effect of N200 with the higher negativity for body-related stimuli versus non-body-related stimuli. The duck here is labeled as object. So these components are early sensory, especially the P100 is visual. However, there is evidence that can be modulated by embodiment and affordance effects. And by affordance, I mean all action possibilities that the object that we observe evoke. The N200 state is a more specific body-related component, peaks around 200 milliseconds in the parietal electrodes, and is higher for body-related stimuli, biological motion representing body, silhouettes, and even faces. We found an effect also related to the frontocentral N100 P200 with a lower N100 amplitude and a higher P200 amplitude in SCI participants. We found a similar effect for a higher P200 overall effect that was higher P200 for body-related stimuli compared to non-body-related stimuli. These components are usually more related to attentional resources and access to the motor representation. Finally, regarding late components, so the rotation-related negativity, these components, as I said, is more related to the mental rotation itself. It increases negativity with the task complexity. We found an effect of the hemisphere that was more negative for the left hemisphere. We found an effect of an interaction between groups in which this component starts to be more negative only in the healthy control group for the rotation that was more difficult to perform compared to the easy rotation. We do not find any other modulation in this component in the other stimuli and in between SCI group. So as I said, this component becomes more negative with the complexity of the task. Regarding event-related spectral perturbation, here we are observing at alpha beta frequencies, so from 8 Hertz to 30 Hertz. On 0, we have the appearance of our target. Here we are looking at healthy control subject versus spinal cord injury to the easy rotation of the hand and the difficult rotation. And this shows just the difference between groups. I'm showing these results only on the regards to the CZ electrode. We found similar results also for the C3, C4 electrodes. So what we find is that spinal cord injury tended to have a higher desynchronization in beta compared to healthy controls. This was true also for the rotation of the feet stimuli. This desynchronization was higher regarding of the rotation angle. And then we do not find a similar modulation for the control stimulus. So what we can conclude? So first, we found evidence of hyperactivity in early stimulus processing. This may be related to several factors. So visual areas are reciprocally connected with motor areas, and in a way they receive subcortical inputs. So this can affect cortical processing, and this can explain why spinal cord injury have hyperactivity in P100. However, the Pareto P100 is also sensitive, as I said, to motor engagement and embodiment processes that can be affected, impaired after spinal cord injury. Finally, inhibitory deficits GABA mediated can affect also the amplitude of the N100, as we find reduced N100 in the SCI group. We found higher engagement of top-down structure, as we found a higher P200 amplitude in the SCI group. This component is associated to attentional resources as well as access to the motor representation and salience effects. Finally, we found an absence of the rotation-related negativity for complex stimuli. So SCI participants seem not to have this modulation for the easy and difficult task. They seem to perform the task with the same amount of cognitive load or difficulty. And this is congruent with the literature on amputees that finds not modulation of the rotation-related negativity in a similar task. Finally, we found a higher desynchronization of beta. Increased desynchronization means that there is reduction in power, and this has been shown in both alpha and beta frequencies during motor execution and imagery in SCI participants. It has been also related to increased motor neuron excitability, and we know that spinal cord injury has an overall increased motor neuron excitability. So what will be the take-home message? It will be that SCI spinal cord injury prevents the exchange between afferent and efferent inputs between the brain and the body. This will affect the way sensory inputs are integrated, as well as the body schema is engaged. I will briefly show now some methodology to manipulate body representation using bodily illusion. In our lab, we are also interested in neuropathic pain and how we can modulate certain mechanisms in order to lower the volume of neuropathic pain symptoms. One way to do this is using bodily illusions. I do not have the time to go into each of the illusions. I will be happy to answer any question if there will be any question. But basically the way illusions work is that they manipulate multisensory information in a way that we trick the brain, and then the perception of the body is altered. This altered perception of the body will give analgesic effect as a consequence in heterogeneous pain population. We have an ongoing study in which we perform two kinds of illusions, the walking illusion and the rubber hand illusion, combined with the anodal stimulation using the TDCS over the posterior parietal cortex. We deliver the stimulation contralateral to the site that's a painful site for the participants. We do 10 sessions of anodal stimulation at 2 milliampere together with these illusions. Before and after this intervention, we are interested in changes in pain and sensory. So we perform pain assessment and sensory assessment, looking at spinothalamic tract, for example. We record also EEG in resting state, as we are interested to see if there is any change in certain frequency at resting state before and after intervention. And we perform a similar task as I just presented related to the body representation. We have two groups, an active stimulation, one group undergoes active stimulation, another groups undergo sham stimulation, which is a stimulation, it's fake stimulation, basically without current. This is with the help of our graduate student, Linda Robaio, and our postdoc, Nicholas Cherap. And it's an ongoing study, so I did not have enough data to present. Our final goals with the overall these projects will be to provide evidence in changes in cortical mechanisms of multisensory body representation in spinal cord injury, and later to focus on any relationship with neuropathy and pain. And finally, also to adapt some multisensory procedure or training to prevent maladaptive brain organization in spinal cord injury, and so lower the volume of neuropathy and pain symptoms. I would like to thank you for the attention. Thanks to our participants, lab members, my mentor, Dr. Widerstrom Noga, and some of the collaborators on this project, the professors William Alexander and Marcello Costantini. Thank you all, and I would be happy to take any question.
Thanks so much, Roberta. What a great talk. Pablo did ask a question in the chat. Pablo, if you're still around and you want to ask the question in person, feel free to unmute yourself. All right, if not, oh, yes, here he is. Go ahead.
Yes, I'm sorry, my English, it's no good. I'm from Chile, from South America.
Thanks for joining us.
I was asking the question because I consider very important the measurement about the autonomic system. Maybe here in your study or in your experience, how difficult it's this control of this or this evaluation.
So I think you're talking about, you asked that question during the first part of Roberta's talk, is that correct? When she was talking about the sensory integration.
So what that would be the question exactly? How difficult would be what?
I think kind of the interplay of the autonomic nervous system and how that might affect.
Oh, how that will affect. Yes, so I believe there is many, this is a very interesting question. There is lots of evidence that show that that's something that will affect also the way we integrate stimuli. It especially depends on the modality that you test. So for example, if you test modality like vestibular or interoceptive smell, versus somatosensory, for example. So they may be very dependent on the modality that you test. There is integration in any of the modalities, so there is no segregation between senses at all in our lives, in anything that we do. So that in a way affects multisensory integration. In our case, we test auditory, vision, and somatosensory using a suprathreshold electrical stimulus. I don't believe in this case that it could be there would be any interference with what we find, but these efforts are really, really strong. So if there is integration, there is integration. If there is no integration, it's not only related to autonomic system alone. But that's a really great question.
Yeah.
Thank you so much. My apologies about my English.
No, don't worry, you're great.
Thank you so much for that question.
Thank you for the question.
If there are no other questions in the chat, does anybody, while we're waiting for any other questions, Roberta, I might ask a question.
Yeah.
You know, looking at body representation and multisensory integration, I'm just wondering if you've ever thought about capturing some functional balance data to see if people with you know, more efficacious EEG findings or more better body representation might also have improved functional balance.
Yeah, I haven't looked at that, but I think that would be really, really great to do, especially if we will be able in the future to develop some multi-sensor integration training and see how that will affect also gait, balance, and force, anything else related to balance. That's a really great question. I haven't looked at that, no.
Well, if you do, let me know.
I'll let you know. We can do something together.
Perfect. All right. Well, thank you to everybody who's joined us today. I also dropped in the chat a link that if you have any type of research that you, we have one more question, it looks like. But I think Patrick has already dropped off.
Yeah, I think that's for Patrick.
For Patrick.
Yeah.
So I'm sorry. Sorry if we missed your question earlier on. But we can actually maybe see if Patrick can answer this later on. But anyway, if you have research or clinical work that you're interested in sharing with us and you're an early career clinician or researcher, please look at the link that I dropped in the chat and apply to have your research shared with us here on our webinar. And this webinar is hosted by David McMillan, myself, Annie Palermo, and Raul Sachdeva. And we are members of Asia's Early Career Committee. And we hope that you join us again for our next episode. Thank you.
Thank you, Annie. Thank you.